Welcome back to Calculus 2. In this lecture, we're going to finally put power series to use and take a look at how we can represent functions by power series. Okay, now this is the start of a very complicated topic for mathematics in general. We're going to right now take a look at the simplest way this works, which is basically starting from this geometric series. In one of our last lectures, we went from taking our basic version for the geometric series, where the general term was a times r to the n, and we mentioned we switched the ratio r from a constant to a variable x, and we arrived at this result. It is basically the geometric series, but we looked at it as from the perspective of having a function, f of x, as 1 divided by 1 minus x. Recall that was the sum. And we spun it around and looked at this as now saying, if we have that function, 1 over 1 minus x, we now have a power series representation for this function, which basically comes from the geometric series. All right, so hopefully this result looks familiar. Pretty much everything we'll be doing in this lecture, which will split into two parts, comes from this result. As we continue through the rest of the course, we'll take a look at other ways to find power series representations that maybe doesn't require using this mathematical result of the geometric series, but that's all left for what comes next. All right, so again, make sure you look at this formula from the perspective of if we have the function 1 divided by 1 minus x, that was previously what we called the sum of a geometric series, then we have this very simple power series representation, x to the n, where the coefficient c sub n equals 1 for all values of n. Now keep in mind, we're only able to apply this power series representation if the absolute value of x is less than 1. We're saying that equivalently, this is only valid for values of x strictly between -1 and +1. Now this is, again, a lot like what we mentioned when we first started talking about power series. It's a way to represent objects in different forms. This might, again, sound abstract, thinking of different ways to represent functions, but it's a lot like when you first learned taking a fraction 1/3, and instead of representing it as a fraction, you can represent that real number with its decimal representation. We're going to be doing the exact same thing, but it's of course more complicated since functions are more complicated than numbers. All right, the main question we're going to be addressing throughout this lecture and pretty much the rest of the course is how do we represent any function, f of x, as a power series? So in other words, given a function, f of x, how do we express it as either of these basic power series, the version containing powers of x, centered at 0, we have our general term c sub n times x to the n, or there might be certain times where we have to represent it as a power series in powers of x minus a when it's centered at some non-zero value. Now, kind of what's going on here, we mentioned very briefly in one of our previous lectures, power series, they can be thought of as being infinite polynomials. So instead of a finite amount of terms with powers of x, we now allow for including an infinite amount of terms, including powers of x. So we can maybe word this a little differently. In red at the bottom there, we can ask, how do we represent a function as an infinite polynomial? If you continue through your journey throughout higher level mathematics, you'll see versions of this question come back as you continue. All right, let's go ahead and get to how all this works. Again, our starting place is this result that we basically saw come from the geometric series. All right, everything that we'll be looking at in this lecture basically comes from this. What I want to do is just kind of break this down into how we're going to use it. And we're essentially going to rewrite our functions to look like this function 1 over 1 minus x. There's that version in the box there where instead of having x in that denominator, so notice we have 1 over 1 minus x. If we have something other than x in that denominator, the part in the brackets or parentheses with the dot, dot, dot inside, if we can rewrite it to look like that, we can just then make a replacement with whatever appears in those parentheses in the denominator. We replace it on that right-hand side in the summation within the power series. So all we're going to be doing pretty much is algebraic manipulations to make our given function look like 1 over 1 minus something. All right, before we get to some I'll say real exam level questions, let's take a look at some rather simple ones. Let's suppose for example 1 here, we wanted to find a power series representation for the function 1 divided by 1 plus 2x. Now pause the video and see if you can make an attempt at this. Think, how might I rewrite this in the form 1 over 1 minus something? Check in a few seconds. All right, let's go through this. Now this one doesn't require a lot of algebraic manipulation. Our basic result for the geometric series has it with the function of the form 1 divided by 1 minus something. Now we have something close, 1 divided by 1 plus something. The something is 2x here. Well, we need to rewrite this to contain a negative, that subtraction, 1 minus the something there. And it's just simply, we can rewrite our function, the denominator, 1 plus 2x. We'll just use a double negative. We'll rewrite that as 1 minus negative 2x. The reason we're doing this, again, is to make it look like this sum result for the geometric series. Now all we need to do is pretty much replace in that result in the box up there in the part labeled very important. We're just going to replace what appears in the parentheses on both sides. That something is minus 2x. And if we have it in that kind of a spot in the lower right corner in the denominator, provided there is a minus, so it fits the form 1 minus something, we just make that replacement on the right-hand side of the power series representation. Again, the something in question here is minus 2x. So we plug that in and we get in parentheses within the summation, negative 2x all raised to the nth power. Now make sure you realize when you make this replacement or use this result for the geometric series, the interval of convergence also changes. So notice in that boxed result, I have the interval part within absolute value that has the something, the dot, dot, dot inside that as well. So you have to replace in there the inside with negative 2x, and we get this interval, the absolute value of minus 2x is less than 1. All right, now you can manipulate that absolute value inequality. You can take the absolute value of each part. Absolute value of negative 2 is just positive 2. We can't remove the absolute value around x since x can be negative, it's a variable. And we can manipulate that to get the simplified absolute value inequality. Absolute value of x is less than 1/2. All right, also notice within the way we're expressing the power series representation, I applied basic exponent rules. Look at the part in parentheses, minus 2x all raised to the nth power. Here, I took the nth power of everything. The nth power of negative 1, the nth power of 2, and the nth power of x. So basically just split that up with exponent rules. All right, and we basically get our result here. We found a power series representation which is valid on the interval of convergence, values of x between negative 1/2 and positive 1/2. All right, let's move on to a second example. This one is a little more complicated since the numerator is not 1. Maybe rewrite this to have part of it look like 1 over 1 minus something. maybe pause the video to give this an attempt. We'll check in a few seconds. All right, these are starting to get a little more complicated, so it might not be as obvious what to do with that x in the numerator. All right, we're first going to try to rewrite this so that part of that fraction looks like 1 over 1 minus something, our basic geometric series result. All right, I can pull that factor of x from the numerator out front. Where we're going with this is the remaining fraction there, 1 divided by 2 plus x. That will use our geometric series representation. It comes out to be a power series involving powers of x. That x factor that we have out front will then multiply into the power series. Multiplying powers of x is very simple. We can add their exponents. That's basically why power series are very nice to work with. All right, so let's take a look at the power series representation for that part in that fraction, 1 divided by 2 plus x. What's screwing this up and messing it up is that 2 down there in the denominator. Our kind of geometric series result has 1 over 1 minus something. We have a 2 there. So a usual trick we can do is, since we want 1 there, let's factor 2 out within the denominator, so that way in parentheses we have 1. But notice if you factor 2 out from x, you're left with x over 2. If that sounds confusing, distribute that 2 back through parentheses, and you should find that you get 2 plus x. We'll be doing a lot of algebraic manipulations very similar to this. Now, this result still doesn't quite look like what we want. We have now 1 and then divided by 1, but not minus something, plus something. So we can use our kind of previous trick. That denominator is at the form 1 plus something. We can rewrite that as 1 minus negative x over 2. The double negative canceling out to a positive to work backwards. All right, that factor of 2 within the denominator, we can pull that out front. Here I have it pulled out front as a factor of 1/2. And now for the end fraction there, 1 divided by 1 minus negative x over 2, that fraction we can use our geometric series, power series representation. All right, so we basically just spent our time rewriting this in the precise algebraic form to make use of our geometric series result. We're going to make the replacement, the part in that kind of result, the part with the parentheses and dot, 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 we replace inside there negative x over 2. If you plug that in there, you plug that in also on the right-hand side of your geometric series result, and you get within parentheses, inside the summation, negative x over 2, all raised to the nth power. And then, of course, for the interval of convergence, we plugged negative x over 2 into the absolute value there as well. All right, that absolute value inequality is equivalent. Take the absolute value of each part, which we've done. You can multiply your 2 over, and you get that equivalent to being absolute value of x has to be less than 2 for this power series to be valid within the interval of convergence. All right, we basically then just simplify. We have kind of, again, a lot of things within the parentheses of the power series, within the parentheses minus x over 2 to the nth power. We'll take the nth power of each part, the negative as well as the 2 in that denominator, and we get this power series result, negative 1 to the nth power divided by 2 to the n, and then that's multiplying x to the n. Again, take the nth power of all 3 terms in the parentheses. Now, what do we do with this 1/2 x? Well, if we apply some basic exponent rules, we can just multiply them in to the power series into the summation sign, x times x to the n, multiply like bases there, you can add their exponents, and 2 times 2 to the n, the factors within the denominator, we can also add their exponents. We can write 2 times 2 to the n as 2 to the n plus 1. All right, and again, we found our second power series representation with a little bit more algebraic manipulations. Hopefully, after these two examples, you're getting the sense for how this works. We basically just try to rewrite our given function into the form 1 divided by 1 minus something. All right, let's take a look at a real example, something that's appropriate for a quiz or exam question. Pause the video to give this one an attempt. This one is very similar to some of the algebraic manipulations we did in the previous two examples. We'll check in a few minutes. Welcome back. Hopefully you did fairly well with this one. I'm going to put up all the work so that way we can get to the next part. We'll go through this individually, step by step, though. Again, the main idea is we're going to try to rewrite this in the form 1 divided by 1 minus something. Now, the 3x in the numerator from our last example, we're not surprised by that. We can pull that 3x from the numerator out front. We're left with then the fraction 1, which we want for the numerator, divided by 2 plus x squared. That 2 is screwing this up. So within the denominator, we can factor out 2. We then get an x squared over 2, but there's still a plus there. So in that final line of the calculation, we're going to rewrite that remaining denominator, 1 plus x squared over 2. We'll rewrite that as subtracting a negative. So that way it fits the form now, 1 divided by 1 minus something. The something here is negative x squared over 2. At this point, we can plug that something in, negative x squared over 2, to our power series representation for the geometric series. And we get in parentheses, within the summation, negative x squared over 2, all raised to the nth power. Now just be careful, we have some inner and outer exponents there. In that case, when you have x squared and then an external nth power, the powers multiply. So if you rewrite that whole term for the summation, you can rewrite this as negative 1 to the nth power divided by 2 to the nth power, and then times x to the 2n. Right, at that point, we basically did all the hard work. It's just a matter of now including that additional factor of 3x that we had out front. So once we found this power series representation, by plugging in negative x squared over 2 to our basic result, we just multiply that 3x into the summation sign, x times x to the 2n, add the exponents, giving you x to the 2n plus 1. All right, this one is a little trickier with respect to the interval of convergence. Again, make sure you're plugging in the something, negative x squared over 2, into the absolute value interval. And we're going to manipulate that. We can actually kind of unravel that and make it look a little bit simpler. As written at the bottom there, absolute value of negative x squared over 2 being less than 1 looks a little awkward. All right, we can take the absolute value of each part. We can think of a absolute value of x squared, interchange the order, there won't be any sign issues. We can rewrite that as absolute value of x, then squared. We can multiply that 2 in the denominator to the right side to get absolute value of x squared less than 2. And then from there, we can basically solve the inequality for absolute value of x, take the square root of both sides. We don't have to worry about the plus or minus since the absolute value, the Version right below deals with that by looking at it as between the negative and the positive version. So we finally get absolute value of x is less than square root of 2, which is equivalent to saying the values of x for our interval of convergence are strictly between negative square root of 2 and positive square root of 2. All right, now hopefully this starts to make sense. Kind of as we continue, we'll start to look at some more complicated ways for this to work. We might need some other tools, which we'll be getting to in kind of the next part. All right, now before we move on to the kind of calculus part, there is a simple way that we can combine power series. Just think of a very basic way to combine functions. You could add or subtract them. And that's going to be the first way that we start to take a look at more complicated functions and how to find their power series representations by trying to combine two existing or known power series representations, like we've been looking at through the previous few examples. All right, now this next part is going to get towards kind of a theorem that applies to manipulating power series representations. And it starts off by supposing we have two functions. We'll be boring and just call them f of x and g of x. And we're going to suppose that they each have a known power series representation. F of x has its coefficients denoted by c sub n. G of x has its coefficients, which might be different, denoted by something else. We'll go with d sub n. The coefficients could be labeled however you want. What's worth pointing out here is that both these power series representations for these different functions are valid within the same interval of convergence. Absolute value of x minus a less than r, where r is the radius of convergence. Now, what might we want to do between two functions, f of x and g of x? A simple way to combine them is by adding or subtracting. So we get our first way to combine power series representations. It's the simplest way and one of the most useful ways as well. We can just add or subtract the two power series representations for each function. Now, the nice thing about working with power series, again, this might all sound very complicated. Just think how you add powers of x. If it's the same power of x, you have like terms, you can just add them by adding their coefficients. So what this first theorem basically says, take a look at your two power series representations for f of x and g of x. They both contain like terms, x minus a to the nth power. We add like terms and also subtract by adding or subtracting their coefficients. The coefficients here are denoted by c sub n and d sub n. Okay, I want to point out before we move on, this theorem, or what we'll be using when we get to the next example, it only works for power series representations that share an interval of convergence. Now, what might happen if the intervals of convergence are different? Well, we might have a larger interval of convergence and a smaller one. We generally have to pick the smaller interval of convergence since that smaller interval is usually contained in the bigger interval. We'll see that in action in the next example. All right, let's take a look at, for this lecture, this part, a final example 2. Again, this lecture will be split into 2 parts. The second part, right after this, will have some of the more calculus-oriented questions where we start incorporating derivatives and antiderivatives or integrals. All right, now this one, again, asks the same question. We have a function given to us, 1 divided by x minus 1 times x minus 3, and we're asked to find a power series representation. Now, as we continue through these examples, we have to get a little bit creative with how we're going to take our given function and use our geometric series result, which has the form 1 divided by 1 minus something. Maybe pause the video to make an attempt at this. Otherwise, check in very quickly and I'll give a hint. All right, again, this one is a little trickier. The hint I'll give, if you want to pause the video to make another attempt, how we kind of split this into a sum or difference of known power series representations is we can perform a partial fraction decomposition. This requires a little bit of mathematical creativity to kind of see why you would want to do that, but take a look at that right-hand side with the individual partial fractions. Each of those can be rewritten algebraically to look like 1 divided by 1 minus something. And at that point, we could apply our known power series representation for the geometric series. At this point, maybe see if you can complete the problem, pause the video to complete the partial fraction decomposition, solve for the values of A and B, and then see if you can, for each partial fraction, find its power series representation. We'll check in again in a few minutes. Welcome back. Hopefully the hint was enough to get you through this. If you went through the partial fraction decomposition correctly, solving for the values of A and B, you should find A is minus a half, B is positive 1/2. So just make sure you're comfortable with that, since we did cover earlier in the course partial fraction decomposition, but it might have been a while ago. All right, what this does for us is it allows us to algebraically rewrite, which is the main theme for all of our examples, as a sum of two simple functions. We have minus a half times 1 over x minus 1, and then we're adding to that positive a half, 1 divided by x minus 3. Now, these partial fractions almost fit the form of our geometric series result, but we want it to look like 1 divided by 1 minus something. We have them both as partial fractions of the form 1 divided by something minus a number. So we're just going to, again, rewrite this. We can reorder the subtraction by factoring out a negative from each part. Notice there's some sign changes. Just make sure you're comfortable with that. We rewrote the denominator in the first partial fraction as basically negative times 1 minus x. Negative canceled out with what's in front. And we did something similar with the denominator x minus 3. We rewrote that as minus the quantity 3 minus x, and then factored the negative out front. Now each of those partial fractions fits the form 1 divided by 1 minus something, and we can apply the ideas of the previous examples for kind of rewriting them to precisely fit that form. The first one fits the form exactly, 1 over 1 minus something. The something's just x. If you were stuck, maybe pause the video to see if you can complete the problem from here. Rewrite 1 divided by 3 minus x to fit the form 1 divided by 1 minus something. We'll finish the problem and check in a few seconds. All right, hopefully you did well. Let's finish. So again, it's that kind of term, the 3 minus. We want it of the form 1 minus something. And we can apply that usual trick, which we've seen in previous examples. We can factor a 3 out from the denominator, which introduces within the parentheses x divided by 3. Again, if you're uncomfortable with that, convince yourself of that by distributing that 3 back in through parentheses to verify that it's algebraically correct. All right, all we have to do now is just bring that factor of 3 kind of outside of that fraction. We can combine it with the 1/2 in front to get a 1/6. And at this point, we just apply our geometric series result, 1 over 1 minus something. We're going to apply that twice. The first partial fraction, 1 over 1 minus x, that just becomes the power series involving x to the n. And then we make the replacement in our geometric series result. We replace the something with x over 3. So we get in the power series x over 3 to the nth power. All right, there's two different intervals of convergence for which these power series representations are valid. The first power series representation for 1 over 1 minus x is valid when absolute value of x is less than 1. Now the second power series, which was the power series representation for 1 divided by 3 minus x, that gives us the absolute value inequality. Absolute value of x over 3 has to be strictly less than 1. And if you rewrite that, you get it equivalent to being absolute value of x has to be strictly less than positive 3. Now, each of those is expressed where we can determine the radius of convergence. The interval on the left has a radius of convergence 1. The interval on the right there has an interval of convergence 3. In order for both these results to be valid, we have to go with the smaller interval of convergence, since it's contained within the bigger one. Rewording that equivalently, we have to go with the smaller radius of convergence. So both these results are valid when the absolute value of x is strictly less than 1. That's the shared interval of convergence. At that point, if the absolute value of x is less than 1, in other words, both power series representations are valid, then we can combine these power series by here subtracting their coefficients. And we get a kind of a combined coefficient in parentheses there, 1/2 minus 1 over 6 times 3 to the n. All right, and that basically does it for our first part. Here, the emphasis was on using the starting place coming from the geometric series and performing algebraic manipulations on the given function to make it look like that form, 1 over 1 minus something. Now, that's very limited in scope. There's plenty of functions that cannot be expressed as 1 over 1 minus something. What we'll be looking at in the next part are examples for other functions that might require the tools of calculus.